Trasmetti dal vivo. And yeah, we are live.
Hello, I warmly welcome you to our 49th webinar by the Academy of Space Renaissance International. My name is Sabine Heinz and I'm the person responsible for our webinars together with Adriano Altino. And on this today is 16th of October. I'm really delighted that you have come to join us to the webinar. Our today's special guests are Werner Grandl. Hello, Werner.
Hello.
Hello. And Jerry Stone. We will hope that he can come and join us. And the topic is space habitats, also webinar regarding the space habitats, SRI Space Habitats Committee. And I also would like to welcome Adriano Altino. He is one of our vice presidents and one of the founders of SRI. Welcome, Adriano.
Thank you very much, Sabine. Welcome, Sabine, and welcome, Werner. And yeah, very interesting this today webinar with Werner Grandl and Jerry Stone. They are chair and vice chair and co-chair of the Space Habitats Committee at Space Renaissance Academy. And today they will give us an idea of the work of this committee. Okay, so.
Okay, thank you. Werner, before I give you the floor, I would like to introduce you to our audience, and I would like to welcome our audience. We have people watching from UK, from Planet Reunion, from Portugal, and from Florida. So welcome, and from Norway. Welcome to everybody, and we are happy that you join us. Werner Grandl graduated at the Technical University of Vienna in 1984 as an architect and civil engineer. He published several papers on studies for space stations and space colonies, utilization of lunar and asteroid resource. And in the early 1970s, Gerard O'Neill's and others developed plans for a large habitat to be constructed in free space that could house 10,000 people. The design known as Island 1 was deliberately restricted to the technology of time, so that no one could suggest that it was fantasy due to requiring materials that had not been invented. However, during the next 40 years, there had been all kinds of improvements and materials, science, engineering, and other areas that could make this program more efficient. So Werner Grandl ran a project of the British Interplanetary Society to re-examine and update the original studies. Construction would not begin with Island 1. We would need to establish a much smaller structure first to house the personnel that will assemble the facilities of the construction, or for the construction. This would demonstrate many of the features of a full settlement, but on a much smaller scale, both in size and cost, as a way of showing the viability of some of the ideas behind space habitation. They designed the initial unit as Island 0. And I would like to give the short bio from Jerry Stone, because I hope she will join, and the webinar is from both of them, so I would like to introduce him too. He is a freelance space presenter and runs Spaceflight UK and gives presentations on a range of topics on astronomy and space exploration all over the UK and abroad. He is a fellow of the British Interplanetary Society and the Royal Astronomical Society. He's also a member of the board of the Space Renaissance International and the chair of the Space Habitats Committee. He ran projects at the British Interplanetary Society to re-examine and update the original space habitat studies. And this became the space project study project Advancing Colony Engineering, which also resulted in a new design for what we called Island Zero, as described above. Werner, the stage is yours. Hello?
Okay. Okay, thank you very much for having me. So I think
You share the screen.
Screen, yes. Okay. Wait a moment. Okay, I think you see my presentation.
Yes, but you have to put it on full screen by running the presentation. Also du musst die Präsentation starten und dann geht's auf dem vollen Bildschirm. It's oben irgendwo. Genau. Ah, dein Computer ist ein bisschen langsamer. Links, wenn er da... Ja, genau. Start mit erster Folie, genau.
Okay,
Okay.
I hope you see it. You see it or not?
Moment, just a second, because I see your computer is a little bit slowly.
I make it different. Wait a minute. So I think you can see it now, huh?
Not yet.
Not yet.
Adriana, do you have it on full screen? Not yet, no?
It's now.
No, I'm sorry, I cannot help you with the LibreOffice because that is not the PowerPoint application. However, you should have a command to show it full screen. No, you stop. You're not sharing anymore. Have to share again.
Ja, und dann...
Okay, it's now okay.
Ja, nee, und jetzt Bildschirmpräsentation und starten. Mach mal nochmal Bildschirmpräsentation mit erster Folie. Ja, genau. Und jetzt müsste es eigentlich gehen, aber irgendwie erscheinen bei dir nur schwarze Rechtecke.
Okay.
It should work like this, but we see like rectangles.
Can you see it now?
Yeah, but we can see it this way, not a problem. Okay. Maybe you can, what you can do is to minimize the lateral windows, you know? Yeah. Okay.
So I do it like this, excuse me.
And the right one too.
Okay, may I start now?
Yes, it starts simply, yes.
Okay, I started simply. So, first of all, I will tell something about the project Artificial Gravity Orbital Station AGOS. It is a study about the simulation of gravity in a rotating space station. I have to stop it once more because I can't. Because this was a failure to. I can't. Now I can't get the next slide.
You have to, maybe you have to show again the left.
Yes, yes, I have. This was a famous.
Fenster, could be Fenster in the menu. Visualization.
Yes, as Fenster.
Fenster in the menu. Click on Fenster. Right, yeah. Fenster.
Well, as you see, we have some technical problems, but we will able to solve it. Please be patient for a moment.
Werner, would you like to send me the presentation? I will show it for you. Send it via email to me.
I think you have already got it, but
Close it simply without yeah.
what
And
more?
but in the meanwhile, send it to Adriano. So
Once more. So this is a.
you have to open it. Yeah.
This is a catastrophe. Yeah, I should not have deleted the left. Why does this not?
If you listen, if you click on page down, it's not going ahead to the next slide. Just click on your keyboard. No, on your keyboard. Click on page down. Page.
No, it doesn't happen.
Ah, that's very strange.
That is very strange, of course.
And what is on the Fenster menu? Fenster, on the right of the menu. Fenster. What is that?
Window, Fenster. Guck mal unter Fenster nochmal. Mach das mal bitte auf.
Fenster.
This will not happen.
No, Fenster. On the right of the menu.
Klick doch mal einfach drauf, Werner. Ja, genau.
What is that?
Oh no, he closed the window. Send the presentation simply to Adriano, and then he can solve it for you.
The best thing, send it to me via email. Okay.
Well, we have to take it like it is.
Okay, we are now waiting that some problems have to be solved. And
maybe you can talk in the meanwhile about IAC Congress in Baku a bit.
Yes, of course, it was an interesting Congress, even if, of course, it was not so big like the previous one in Paris, but that was obvious because it was okay. In Paris, I think, was maybe one of the biggest participation in the history of IAF. However, Baku was quite interesting. It was also participated by many companies, and there was an exhibition center with a good participation space agencies and by companies and by organizations also. Unfortunately, we couldn't have a boot this year for logistic problems most of all, and but yeah, we were able to make a good. Sorry, I have to admit Werner again. We were able to make a good propaganda for the 18th SDG, gaining several new supporters of the idea, and yes, and there were several interesting presentations. We also had Elon Musk live in discussing with Clay Mowry, the president of the IAF, about the situation now, the status of the Starship, and waiting, of course, for the FAA permission to launch the second tentative to go to orbit for a Starship. And yeah.
Werner, you can leave it like this, and we can see the fold. And leave it like this. Lass es einfach so, wie es jetzt ist, und mach dann einfach die nächste Folie. Ja?
Das
ich glaube, das kann man.
Nicht. Das funktioniert nicht.
Ach so, weil du die nächste. Hast du Adriano schon? Ja, hast du es Adriano schon geschickt?
Ja, es ist leider zu groß, um es ihm zu schicken. Das ist das Problem.
Schick es per V-Transfer, dann geht es ganz schnell.
Ja, das schaffe ich hier gar nicht. So, Folienübergang, Animation.
Did you send it to me?
The file is too big.
File is too big.
Too big, okay.
And now he cannot refine where the slides has to be. Ansicht, ja, mach mal Ansicht.
Ja, das nützt nicht. Ich bin schon dabei, Seitenleiste, Folienlayout.
Geh noch mal bitte auf Fenster.
Nein, das kann ich gar nicht sehen. Seitenleiste ist nicht sichtbar.
Du hast ja ein Fenster zugemacht, also geh bitte noch mal auf Fenster. Lass mich mal kurz gucken, was da steht.
Kannst nicht machen.
Na, da oben ist doch Rechtsfenster.
Ja, aber das steht ja anderen Sachen.
Ja, mach mal bitte noch mal, geh mal bitte noch mal auf Fenster da. Nee, nicht zumachen.
Ja, es geht nicht, ich sehe Fenster nicht.
Okay, dann schick es per V-Transfer. Öffne mal deinen Browser, also einfach.
Warte noch mal.
Listen, Werner, I give you an idea. Save it as a PDF. Okay?
I can send it PDF.
Save it as a PDF.
Yes,
then you can use the PDF instead of the presentation.
Yes, okay. So, but I have to.
Maybe you already have it as a PDF, could be.
You have it, but
you don't know where.
So just a moment.
Okay. I see it. I see it in your desktop. Space habitats. Is that
yes,
PDF?
Yeah, it's there.
Open it.
The PDF, open the PDF.
Yes. But the question is if the audience can see it.
Yes, open the PDF, please.
Yes, it is open.
No, we cannot see it.
It is open.
So you have to start again the sharing, choosing the window of the PDF because we don't see it. We only see your desktop.
Also you have to, du musst nochmal den Bildschirm teilen, nochmal rausgehen und dann den Bildschirm teilen. Ach so, das öffnet sich jetzt langsam. It's opening slowly. Aber du musst trotzdem nochmal rausgehen und nochmal reinkommen.
Habe ich schon gemacht. Das habe ich schon gemacht.
So, jetzt nochmal Bildschirm teilen und dann die geöffnete Datei dann reinholen.
Jetzt ist es da bei mir.
Bei dir, bei uns noch nicht.
Ja. Das ist ärgerlich.
We cannot see it.
Ja.
Also wir können es nicht sehen.
Please make a right click on the PDF file. Right click.
Rechtsklick.
Maybe I got your presentation.
You got it?
Yes. Okay, I will do it.
Okay, stop sharing. So to our audience, thank you for being so patient, and I hope we will solve the problem immediately. Adriano is opening it, and he is our computer specialist, and I trust him that he will open it.
Yeah, just a moment. I'm
Yes.
I'm coming.
In the meanwhile, we have people from Kuwait and Boris. From where do you come from?
Allora, ci siamo, eh? Un momento. You full screen mode. Yes. And now I have to share.
Perfect.
I have to share.
Normally we tested before, but this time it was all so short. We had some technical issues, but Adriano managed it. Yeah, Adriano.
Can you see?
Yes.
Thank you so much.
Okay, you can start, and when you want a new slide, please tell me next slide, okay?
Okay, thank you so much, Adriano.
Thank you very much, Adriano. This is a very, very good solution. So, okay, I will start. So, today I will present you the artificial gravity orbital station AGOS. I have no problems with my writing. It is dealing with the simulation of gravity in a rotating space station. Next slide, please. Yes, thank you. So, first of all, I show you two examples for rotating orbital space concepts, among many others in the 20th century. On the left side, you can see a NASA design from the 1970s with the use of the space shuttle external tank that you can see in the center of the station as a central hub. And then around this hub, the space station should have been built. As an interesting example, on the left side, you can see a very early design from 1928 by Hermann Mordung, who was an Austrian officer in World War I. And he has designed this concept in 1928. It was called Weltraumrad. It was also a rotating structure, about 50 meters in diameter. And he made also a construction and the design to collect solar light with a mirror, with a parabolic mirror. Next slide, please. Okay, what can we call artificial gravity, or AG? It is the simulation of gravity by centrifugal force. It is not a real gravity. It is just a simulation of gravity by rotation. The effects of microgravity on the human body, if an asteroid is staying longer than a couple of weeks in space now, for example, on the ISS, there is, for example, loss of bone, loss of red blood cells, fluid shifts inside the body, and the cardiovascular and sensory motor deconditioning may occur. A rotating space station can provide up to 1G artificial gravity. And the bigger the radius, the better are the conditions. We have also think of the so-called Coriolis acceleration. This is a physical phenomenon which occurs on the surface of rotating bodies and causes transverse motion of objects. Now we look at the so-called comfort box. This is the figure on the right side. It was developed by a NASA engineer. His name was Jesko von Puttkammer in 1987. They had made some measurements and some experiences, and so they have developed this concept of the so-called comfort box within humans may live in such a rotating space station. According to Jesko von Puttkammer, the rotating space station should have a minimum radius of 30 meters and the rotation rate, maximum rate of 4.5 rounds per minute. You can see it. You can see it on the right side. There is the so-called comfort box. Next slide, please. So we have developed a project which is called AGOS, Artificial Gravity Orbital Station, which could be a possible successor of the present ISS, because the present ISS will be decommissioned in 2030 or in 2035 or something like this. Now, our design contains mostly of hard shell aluminum cylinder with the entire furniture and the equipment inside. The cylinders have approximately 80 meter length and are 7 meters in diameter, and the weight is about 20 metric tons. The transport in the lower Earth orbit, which is about 450 kilometers above Earth's surface, we propose to use SpaceX launchers, which are in parts reusable. So the first stage of the SpaceX launchers is already reusable. The assembly of AGOS should be done in stages. On the right side above, you can see the initial stage 1. It contains of 4 rotating living quarter modules, which provide 90% of Earth gravity. It's of course a simulation. 4 zero gravity modules along the central axis of the station, and 1 docking module for spaceships, which is shown in green color on the right side of the sketch. Then, of course, we need some connecting tubes and structural framework to connect all the tubes. And last not least, we need 1,600 square meters of solar panels and the total launch weight may be about 270 tons from Earth, metric tons from Earth. The entire diameter of the construction is about 102 meters. The rotation rate is not more than 4.2 rounds per minute. 16 launches, including robots for assembly and the first crew, are necessary to establish the initial stage 1 of Argos. The first crew contains of 24 persons, and then this station can be enlarged in stages, one by one stage, and the final stage is a rotating ring with 32 living quarter modules with a crew of approximately 180 persons, including astronauts, including scientists, including, of course, space tourists, and so on. It's figure 2 on the right side of the bottom. Next slide, please. Once again, the evolution of Argos. The first picture is stage 1. The second one is a small enlargement with 8 modules for living. And the third picture is, of course, the final stage, the rotating ring. Argos can be enlarged in stages. All components are modular, and the final stage is a closed ring of parallel living quarter modules for approximately 180 inhabitants. Next slide, please. After some years or after some decades, when the final station is finished and we have industry and mining on the moon, and we can get material from our moon, we can build a rotating agricultural sphere which can be combined with Argos. When lunar material is available for construction, an agricultural sphere can be added to Argos to provide nutrition for the inhabitants. Artificial lighting by a central cylinder, it is shown at the figure left below, nutrition for the inhabitants. Artificial lighting by a central cylinder can optimize the harvesting of vegetables and fruits during an annual period. And we can also make aquaculture to provide fish, mussels, and shrimps. If you look at the left picture, you can see the aquacultures in blue and the vegetable cultures in green. Of course, it needs a very big volume of air, about 200,068 cubic meters. So this is very much, and we cannot bring all this material from Earth. We have to use material from the lunar, from our moon, or from asteroids in the future. Now, the construction of the rotating sphere can become a precursor technology for future spherical or cylindrical human settlements, like the projects of Gerald O'Neill. So this is a precursor project for Gerald O'Neill projects. Yes, so next slide, please. Now there are some details of the living quarter modules. Each module has 2 floors. It has a diameter of 7 meters. The length is about 18 meters, and it is designed for 6 persons, for 6 astronauts or even space tourists. On the left side, you see a section with the 2 levels. On the right side, you see a drawing of the upper floor and the lower floor. The upper floor is the living and working area, about 77 square meters for 6 persons. I think this would be enough. And the lower floor are the so-called private rooms. Each astronaut, each person has its own room, its own private room, including a shower and a toilet. And the 2 floors are connected by a ladder. So you have to climb up and down. You can see it on the left side in the section where there is the opening and the ladder in the section. There is a third small picture. This is, of course, a cutaway drawing of one of the cylinders. There are, in this case, there are 2 cylinders combined. So, yes, next slide, please. Now, the structural components and the mass. This is a key problem. Our goal is low mass, high stability. All structural components are made of thin aluminum sheets and trapezoidal aluminum sheeting. The sheets are only 0.5 millimeter thick, and the structural mass of such elements are approximately just 10 kilograms per square meters. You see it, figure 1, this is a bulkhead. And in the figure 2, you see a detail of a structural component. There is a trapezoidal sheeting between thin aluminum plates. So it is extremely lightweight. And the spacing between the thin plates can be filled with foam glass for heat insulation. Of course, this foam glass can also be used as a shelter against micrometeorites, because the micrometeorites would stick into this layer. Next slide, please. One of the main problems for the construction of such a station is the so-called rotor joint. It is the connection between the rotating parts and the central non-rotating hub. We propose a so-called magnetic liquid rotary seal. It is a hermetic seal. It uses a so-called ferrofluid. This is an oil-based liquid which is suspended by a magnet, by a permanent magnet, and this fluid is filled with small pieces of iron, so it can be suspended by a permanent magnet. You see on the sketch, you can see in detail how this rotary seal may be constructed. You see the rotor, the stator. The rotor is shown in green and the stator is shown in red. And there must be also an auxiliary fluid tank, of course, if there are any leaks. Then between these two rotors and stators, there are ball bearings, and the seal gap is filled with the fluid. Of course, between the rotating cylinder and the non-rotating cylinder, there must be an airlock with a fire door. Well, principle for security and safety of the crew. Additional ball bearings provide the centering also of the rotor within the seal gap. There is a company which is called Gravity, and this company has developed this machinery. So, next slide, please. Okay, this slide is called Payload and Launches for Argos Stage 1. This is the initial stage of the crew of only 24 people. You see the living quarter modules, they have a weight about 20 tons. This is the launch weight. You have the central rotating modules with also 20 tons launch weight. We have the central non-rotating modules, which carry much more machinery, so they have a weight of 22 tons. We have the so-called docking module. We have the radial spokes, which have 3 meters in diameter to carry an elevator. We have also the connecting tubes, and we have structural framework to stabilize the entire construction. And we have the 1,600 square meter solar panels, which are, of course, lightweight construction. Then, of course, we need an additional launch for machinery, especially for robots, for the assembling of the station. And, of course, a launch for the first astronaut crew. So we have a total of 16 launches at minimum for a weight of 270 metric tons for this stage 1 of Argos. And we use, of course, or we are proposing to use the SpaceX launcher, the Falcon launcher, to bring these modules into low Earth orbit, about 450 kilometer altitude. Next slide, please. Oh, interesting question. Where could the budget for Argos come from? Now, of course, these data from the year 2018, but I think they are now also valid. How much is the ISS in 24 years? The construction expenses is about $60 billion, and the operation expenses has been until the year 2018 about $40 billion. So the total cost were approximately $100 billion until the year 2008, until the year 2018. So the expenses per year are or have been about $4 billion a year for the ISS. Now we compare it to the annual expenses for armament and warfare in the year 2018. Nowadays, I think it will be much higher than then. In the year 2018, the USA had a budget, a military budget of $650 billion. Then comes China, then comes the European Union and Great Britain, Russia. So every year, the superpowers and the big powers have $1,152 billion for warfare and for armament. If you compare these data and these costs, you can easily imagine that if we take just some of the money for our space projects, they could be easily realized and made. Now a timeline. We suppose approximately 10 years for the design and the production, and 2 years for launching and assembling of Argos Stage 1 with its 270 metric tons in the best case. Scenario about 2035. Of course, if you make all these launches within 2 years, there is, of course, international cooperation necessary. We have to use not only American and European rockets, we have also to use Russian, Chinese launches, and maybe of some other emerging countries like India and so on, which can also have launchers to bring our hardware into space. Next slide, please. So, when we have learned some things, some essentials, and some essential things from our Argos station or from any other rotating space station, in the far future, maybe in the next 50 or the next 100 years, we can, for example, build asteroid habitats inside near-Earth asteroids. This is now a little bit utopia, but I will show it nevertheless, my ideas. In the far future, near-Earth asteroids can be mined to utilize their mineral resources. When the mining process is finished, we can build a rotating habitat inside the asteroid's hull. For example, we have taken, this was a project with the Vienna Institute of Astronomy some years ago. We have taken the asteroid 2008 EV5 with 450 meters in diameter and the bulk density approximately 3 grams per cubic centimeter. It is like the density of natural concrete on Earth. The mass of this asteroid is approximately 1.4 billion tons, and it is an asteroid of the so-called S-class, which means it is a stony asteroid. Next, please. Next slide, please. There are two sketches which may seem to be a little bit utopian, but I think within some decades or in the next century, we can make it as well. On the left side, you see a section through a prototype asteroid colony for about 3,000 inhabitants. First of all, the asteroid is mined, and approximately 50% of the asteroid's mass is mined, and a hollow crust remains from the asteroid after mining. And inside this hollow asteroid, one can build a rotating asteroid colony in the form of a torus. It can be enlightened with natural sunlight. You see it on the top of the picture. The incoming sunlight is caught by a parabolic mirror array and is beamed into the center of the asteroid, and there is a so-called light distribution cone with facets of mirrors which can distribute the light through windows inside the rotating colony. On the left side, you see the section. On the right side, you see a small cutaway drawing. And you see the green areas, those areas for habitation and also for agriculture. Yes. Next slide, please. The rotation rate of the torus is approximately 4 rounds per minute. This is a maximum. Maybe it could be a little bit smaller, I think 3.5 rounds per minute or so. And it is made by electromagnetic levitation bearings. The gravity simulation will be about 90% of the terrestrial gravity. Once again, it is just a simulation. It is not real gravity. The Coriolis acceleration is minimized. It is approximately 0.05 g. The population is about 2,000 at the beginning, and can be increased to about 3,000. Nutrition is made by vertical farming and by aquaculture. The goal is a closed air and water cycle in the future. Now, this is a very future project. Maybe it will be made in, I think, the next 100 years. Maybe we can build such a prototype project. There are hundreds of near-Earth asteroids which can be used in the next centuries for such mining activities and for such small colonies around the Earth in the solar system. Next slide, please. So this is all. I thank you very much for your attention and thank you for having me. And I apologize once more for the delay at the beginning.
Yeah, thank you so much for your presentation. Thank you, Adriano, for your help and for solving this problem so fast. And I also would like to welcome Jerry Stone. Hello, Jerry. I presented you already or introduced you already to our audience. Would you like to add something, or do you have another presentation?
Yeah, I do have a presentation about Island Zero.
Okay. The question is, shall I take quick the questions from the chat for Werner, and in the meanwhile you can prepare a little bit?
Yeah.
Yeah.
Yeah, I've seen what's in the chat.
But Werner have not seen what is in the chat, so I would forward the questions to him. Werner, I also would like to welcome David from London. We have people from Pennsylvania watching. And yes, and Anna Larsen is asking, isn't there a lot of information missing here about why a larger and more functional cylinder can't be built directly? And he added, this is not a rotating cylinder, but rotation of cylinders.
The cylinders are so small because I think it would be useful to use small cylinders because the assembling is very easy. And if you are building a big cylinder, it would be very difficult from the engineering point of view. And of course, the greater a cylinder is, the more oxygen you need for the air. So I prefer small cylinders and modular cylinders to build the first rotating station.
Yes, and the answer question is, isn't it already clear fact that all the fuss about that, what it costs and who will pay is the biggest obstacle to our long-awaited space establishment?
An obstacle? I don't think it is an obstacle. Yes,
No. Yeah.
we have
Okay.
established space agencies, yeah, and they are very skeptical about such projects, of course. Yeah? So it is our choice and our duty from the Space Renaissance Academy to promote such projects in the long run.
Yes. Adriano, do you have a question before I give Jerry the floor?
Oh, well, yes, no, more than a question, I think some consideration that, of course, if we have to start experimenting artificial gravity, therefore we cannot start building a very big infrastructure. I think even a small space station rotating would be a giant step ahead, considering that for 60 years we only experimented zero gravity, and so we have to start. So of course everything should be scaled in a growing experimentation toward big infrastructures for thousands of people, of course, and more. Yeah,
I agree with you. Okay, thank you, Werner. I hope to have you here because I think we will discuss a little bit later on. Jerry, I would like to give you the floor for your presentation. You may share the screen. And I'm really happy that you have come to join us. Yeah, and to see you.
Okay, let's...
I have to apologize because Zoom is making strange thing with the you know, the subtitles, the transcript. I don't understand why it tries. Zoom is trying to give a German transcript and mix it with English transcript. I don't know what happens with the new release. Maybe something strange happened. So I will try to fix it if possible for the next next webinars. But today I hope you will understand and forgive us.
Okay, so I think I have to open the presentation first and then share the screen.
Yes, exactly.
You were sharing just 30 seconds ago.
Right, let's go to...
Yes, but he has to open first the presentation
here,
before sharing.
Now share and...
If you have problems, just send your presentation to me. And
no, I don't think I can because it's a keynote file and not a PowerPoint. Hold on, let's see what that comes up with. Right now, okay,
excellent.
Yes.
So you can see the initial screen. So here we go. So I am Jerry Stone and I run Spaceflight UK. And this is about a part of the space project, which I shall explain. And it's particularly about Island Zero. So this is Gerard O'Neill, who back in the 70s put a question to a group of new students asking them, is a planetary surface the best place for an expanding technological civilization? This was meant to be the first of a number of questions that they would investigate, but in fact, they never got on to the second question because this one was so much of interest. So they did some research, did some studies, and came back with an answer to this question, which was no, not a planetary surface. Instead of being on the surface of the Earth, the Moon, Mars, or somewhere else, they decided that the best place was out in free space. And the main reason for that was on any planetary surface or on a moon, you will lose the sun for an average of 50% of the time. And out in free space, you can have the sun continuously. So you can use its light. You can also use its energy to be turned into electricity to provide all of your power. You could also concentrate the sun's energy to provide about 5,000 degrees, which would be enough to process practically anything. So where should this be? Well, if that's the Earth and here's the Moon and its orbit, if you draw a line between them, then 1 and 2 points are either side of the Moon in its orbit. Now, they're called L1 and L2 because they were determined by a mathematician called Lagrange. So these are Lagrange points. Now, what's interesting about these 2 points is that although L1 is closer to the Moon, closer to the Earth than the Moon, and L2 is further away from the Moon, you would expect them to orbit the Earth at different times to the Moon, L1 being faster and L2 being slower. But actually, at these particular points, the gravitational forces of the Earth and Moon combine so that they stay in the same relative positions to the Moon. So that's why, if this is not the Earth and the Moon, but the Sun and the Earth, L1 would be great for pointing towards the Sun. L2 is great for pointing out to space. There's also an L3 over the other side of the orbit, but that's not really a lot of use to us. Now, all 3 of these points are unstable, though. If you start to move away from them, you will continue to move away, which is why spacecraft placed at L1 or L2 need to have onboard engines to fire now and then to keep them in position. However, there are 2 other places. 60 degrees in front of the Moon, L4, 60 degrees behind it, L5. And these points are stable. If you start to move away, the gravitational forces of the 2 objects will bring you back again. So it was decided that these would be good places for large-scale space habitats. So this was the first design that was created. The habitat itself is the spherical section in the middle. Just behind it and in front are mirrors And together with the circle of mirrors that surround it, they would beam sunlight to the interior through large circular windows. At the back, you can see behind the radiators, there are other mirrors and also processing areas. And there's something similar at the front. You can see the radiators, and also at the very front, a dish to focus sunlight. The series of rings in front of and behind the main sphere are the agricultural areas. This was another design known as Island 2, which is a torus shaped habitat. The section in the middle is a processing area, and it also bounces sunlight from those angled mirrors to the interior of the torus, and up above it is a large mirror to bounce the sunlight down to there. And these are the Island 3 habitats. These are the big ones. They are 4 miles in diameter, 20 miles long, and each with 3 land areas interspaced with 3 large windows which receive the sunlight bounced off the angled mirrors. And all the small sections in a ring around the front, those are the agricultural areas. The advantage of them being separate means that you can have the same crop at different growth levels in each crop. So you can always be in a position where a particular crop is to be reaped. And because there are no seasons here, it means you can keep growing and you'll probably get 3 crops a year, whereas on Earth we'd only get 1. So strawberries all the year round. There's a possible inside view down one of the cylinders, and without having huge cities in there, you can still have over 1 million people. So coming back to Island 1 then, here's a view through one of the circular mirrors to the inside. And as you can see, you have rivers, houses, plants, trees. So we could, and also there'll be some animals. So we can take all the plants we want without having stinging nettles. On the animal side, we can take bees to make honey, but we can leave wasps behind, so we can have our barbecues down there in safety. So what would they be made of? Well, we know that lunar soil contains oxygen, so we could use that to breathe. Silicon for the windows, iron, aluminium, magnesium for construction, and others, including titanium and so forth. So we can build this out of lunar soil mostly. The advantage of that, rather than sending material up from Earth, is, of course, the huge amount of energy required to send things from the surface of Earth. So here's a way of getting the material from the moon, because the moon has no atmosphere and it has energy from the sun. We can have an electromagnetic launcher, and the area to be, I won't say mined, because we only need to go down 7 meters, but an area about 200 meters square, 7 meters deep, would provide the 500,000 tons needed to build one of these units. So the original design was restricted in 2 ways. The cost. It had to be able to be built for no more than what it cost to do Project Apollo. So nobody could say, we can't afford it. Also, technology. It was deliberately restricted to the technology available at the time in the 70s. And that was so that nobody could say, well, it's a nice idea, but it depends on this, this, and this that we haven't invented yet. So a few years ago, I thought, all right, since the 1970s, our technology has improved enormously. We have new alloys, we have new materials, we have things that hadn't been invented back then that exist now. And our computing power has grown several orders of magnitude. So I thought, if we were to do this today, we could do it far more efficiently and probably cheaper. So I set up a project at the British Interplanetary Society, which I called the Space Project, Study Project Advancing Colony Engineering. So that's just my sense of humor. And I gathered a group of volunteers, and we started looking into this. And one of the things we came up with was, you've seen Island 1, Island 2, and Island 3. But to do Island 1, we would need assembly facilities out in space to actually put the thing together. Before that, we would need manufacturing facilities to create the parts that would be used, windows, beams, and so on. And to do that, we would need material processing facilities to turn the raw material from the moon into metals, glass, and so on. And together with all that, we would need offices, workshops, and living quarters for the crew. Now, originally, Gerard O'Neill expected that we would need about 2,000 people for the manufacturing team. And our team decided that we would be surprised if, because of the advances that we have, and particularly in robotics and also manufacturing things automatically from raw materials, it would probably be unlikely that we need more than 200 people. And as with any project involving space, the greatest cost is that of the people involved. So we reckon the cost will be a lot lower. So we decided also that you wouldn't just simply start building Island 1. You would need all of those facilities that I've just mentioned, and for the living quarters for the staff who were going to build those, we came up with a smaller habitat, which we called Island 0. This would have simulated gravity. One reason for that would be for the health of the crew. On the International Space Station, all the crew needs to carry out 2 hours of exercises every single day. If they lived in simulated gravity, particularly if most of the time spent there, which would be sleeping, is under a simulated gravity, that will help them enormously. It will be made up of modular components, not quite like the International Space Station, but there would be only a very few types of components, as I'll show you. They would grow their own food, mostly, we hope, and they would build the manufacturing facilities. So the main living modules would be inflatable, 15 meters by 4.8 meters diameter. And we originally thought that they could be carried up in reaction engines Skylon spaceplane devised by Alan Bond. This can carry materials into low Earth orbit initially, although of course it can also take a booster in it. And then having released its payload, it will come back to Earth and land on a runway as it also takes off. So it's fully reusable within about 3 days of its previous flight. So there's the unit, and being inflatable, it could be compressed to that size. So that's the payload bay of Skylon, and that could fit 4 at a time. So we assumed initially that it would be arranged in a rotating object like this. However, I then did some calculations about the speed of rotation compared to the radius of the unit and the resultant effective gravity. And for the size that we thought it would be, we thought the pull of gravity was not going to be right. So we came up with a radius of 200 meters would give at just 2 RPM would give us a pull of gravity of 0.9 meters. Now, one thing that I asked at the very beginning of the project was, it's always assumed that all rotating habitats will rotate at 1G. So we could do that if we went out to 225 meters. But I asked the team, not for an immediate answer, but something that we might look into, was, do we actually need 1G? What about 0.9, 0.8, even 0.7? If we did that, then the structural forces on the habitat would be lower. So the amount of material to build them would be less. Also, the forces on the inhabitants would be less. There'll be less pressure on their skeleton, on their muscles, on their heart. But the question is, at what point does decreasing the gravity pull become a problem rather than a benefit? And that is a big question. So 200-meter radius would mean we'd need 84 of these units to do a full circle, which it means it's no longer a low-cost item. But like this doesn't work. So we said, do they need to be a continuous run? Why not do it like that? And that way, we can have them at 200 meters out. We would also need an outer circle, but that would be smaller diameter. So that's with 8 units. And obviously, over time, we can add more. So this is what the inside might look like with several floors. That shows the position of the connecting tube around it. And rather than vertical ladders, we could put steps connected to the outside rim of each unit between each floor. So that would give a volume per unit, 270 meters squared, 8 units, 2100, and compared to the Destiny module on the International Space Station, as you can see, it's a lot larger. So the total ISS habitable volume is 900 cubic meters, whereas ours, just with 8 units, would be 2100 meters, cubic meters. Now, to get from the central hub to the outer units, we would have a series of long units fitted together in a curve like that. So that from the center, where you'd have weightlessness, you would go down and the weight would slowly increase till you got to the outer edge. So we would have 4 of these, and the whole thing would rotate, and with central area docking ports and solar panels, as you can see, this is what it would look like. So we have the space project, and we have a logo for it. That was our logo, and here is a theme.
All world colors. The chance to begin again, and the golden land of opportunity and adventure.
So how long will it take to do all this? Well, we could produce Island 0, bearing in mind we have to start the construction of the parts here on Earth, but with a fully reusable spacecraft booster, such as we do already have, even though we don't have Skylon yet, we could probably put that together in just a couple of years. But we also need to to get the lunar surface units. However, I think that we need to do an Island Zero in low Earth orbit simply to get more experience, particularly of living in space under simulated gravity, which we have never done before. So this is a summary which I put together about the space project and about Island Zero. And if anybody is interested in a copy, then contact me at jerry.stone2001@gmail.com. That's Jerry with a J, jerry.stone2001@gmail.com. That's it. Thank you very much.
Thank you so much, Jerry, for this interesting presentation. We also get another guest in our round, Julio Resende. He is from Brazil and also member of the board. Yes, we know each other all well. Ina Larsen is commenting one thing. Moment, he has many remarks here. Isn't it precisely speculation about what is financially profitable that has held us back all along? Also, yeah, he is talking about money, and he is complaining or saying, when will there be a serious explanation as to why there is no focus on creating our existence in space free of a monetary system which expands all efficiency? And why is this so easily ignored? So, yeah.
I can mention that Gerard O'Neill said in his terrific book, The High Frontier, that their studies showed that when you had an Island 1 in full operation with 10,000 people on it, that it would be self-sufficient, entirely self-sufficient. They would definitely trade with the Earth, as any city would, but they'd be able to grow their food in the agricultural rings to support themselves. They would be able to continue to get raw material from the moon. In our study, we have added that a lot of material will probably come from asteroids, particularly things that are fairly rare on the moon. But yes, it would be fully self-sufficient. However, of course, there is the time taken to actually carry out the construction, and during that time, then there will be very substantial costs. So what is needed is, as I said, the cost similar to that of the Apollo project. Well, if we take that as being the equivalent of 28 billion now, there are people, organizations now that could theoretically put money towards that, and on the basis of them getting something back once the construction is finished and it's in operation. So yeah, it's possible.
Yes, he's referring more, I think, He says, I don't think any advanced cosmic civilization that can travel between the stars use something as primitive as money. It reduces quality and limits projects. If I'm wrong, please tell me why. Also, I think he is referring to later phase when we are settled in space, more or less. But I think we don't know. But yeah, I let you give the answer.
Well, we're not going to be traveling to the stars for quite a while yet.
Pardon?
I think we won't be traveling to the stars for quite a while yet.
Yes, I think so too. Adriano or Werner?
Well, I think we have seen two very interesting, similar for some the concept at the end. The concept is the same: to make an habitat to rotate, making with modules, because we cannot build in one only piece, and very similar concepts. And what is my concern? My main concern is that. Is just an intuition, because we didn't experiment nothing of that so far, is how much the Coriolis effect will affect the human perception of the space and of the equilibrium and of when you stand on your feet, you have awareness of the gravity and where you are and so on. But the smaller the habitat, the smaller the rotating habitat, the bigger the effect of the Coriolis. So this says the theory, because we didn't experiment so far. But okay, so
that's another reason why we didn't want a small radius of it. We've gone out to 200 meters.
We have to make it small in order to start experiment, but not too small, because if we make it too small, I think it will be like to stay inside the wash machine, very disturbing effect. So I think this should be the concern when we start to design a real thing. So maybe the 200 meters diameter could be. And yes, one question to Jerry: why in your in the last model you show with 8 modules connected by a ring?
Yes.
Okay. Why the modules are vertical respect the center? Couldn't this module, however, be horizontal to the ring? Because then I think it will be the habitat 8 meter or 15 meter, I don't remember, long, will be, let me say, more comfortable than to have 4 floors in a vertical cylinder.
Yes, I should have included that. We did come up with that as a possibility, as an alternative. The advantage is that you can make more use of the floor area.
Yes. Yes, and even to have an environment that is more, I think, more comfortable from the point of view of comfort and habitability. But
really, more investigation needs to be put into this, really from a space organization, ideally.
Yeah, and another question. Of course, this I understand that this is a project of the British Interplanetary Society. So you are thinking about Skylon, and Skylon is a very ambitious project, because it is a single stage to orbit, that is one step ahead with respect to Starship. That is a two fully reusable stays to orbit, maybe more realistic considering the technologies we have now. But Skylon, I know for the little I know about Skylon project, they want to use a one only engine.
Yeah,
It has a double way of working with the
end of each
air
week.
braking and yeah, I don't remember exactly the technology.
Sabre engine. So one thing that has prevented the development of single stage to orbit craft is the amount of fuel needed. But they have all been on fuel which is held purely within the craft. Now with Skylon, they do not rely on onboard fuel for the launch, not purely on that. The Sabre engines start off by acting as jet engines. So they take air in the front, blow it out the back. And that means they don't have to carry the fuel for that on board. I mean, obviously to run the engines, but the air is brought in and blown out again. And then when they get fast enough and high enough, the engines actually, they put a cover over the front of the engine, and they use the onboard hydrogen and oxygen to take them up from there to orbit. But because they haven't had to carry that amount of fuel up with them, they can do it in one stage. And that is the remarkable thing. It's the engines, which are, they first of all, the air that comes in gets cooled down to minus 100 degrees within 1,000th of a second. And that technology is amazing. That has all been tested and proved, and it has met all of the tests put to them by the European Space Agency. It's passed all the tests and it works exactly as it should. So they'll have to carry
how far are we from seeing the Skylon to fly?
I'm afraid it may be at least another 5 years. But I mean, even if it takes 10 engines, when that goes into operation, now this is something weird, it needs a especially hardened runway to take off. But when it comes down, it can actually land on grass. Its initial design is as an automatic unmanned craft, but there is also a manned version planned, and the payload bay can be a multi-person unit as well. Once it does launch, then when it's fully up to operation, it can come down, land, have the minimum of maintenance, unlike the space shuttle main engines, which cost so much and so much time to look over. It could then be maintained and refueled and fly again 3 days later.
Okay.
And the result will be that when it is in full operation, the cost of reaching orbit is going to plummet.
I see. However, okay, the project, Island Zero project stands up. However, even if we, maybe I don't know, maybe next year, or in 2 years the Starship will be operative, so you can recalculate the cost using Starship. Is not that the problem, I think. No, Island Zero can go ahead. However, if there is a decision about that. So the next question is, was Island Zero project presented to ESA maybe, or are there some possibility that it will get financed and start at least a stage A feasibility?
Right. We haven't made an official presentation to ESA, though I've sent my my summary to some of ESA's staff. But yeah, I would love to do a full official presentation at an appropriate opportunity.
Yeah, maybe we could. Yeah, maybe we could do something about that. I think we already talked about that in our committee to contact some ESA officer, and yeah, perhaps we could also talk with Jan Werner. You know, Jan Werner is our member, honorary member of SRI, and yeah, he participates to the Space Law Committee. And even if he's anymore the Director General of ESA, but maybe he could still put a word for that. So let's think about that. Yeah. Okay.
Yeah, I think we can, there are no more questions in the chat. I think we can close this evening. I really thank you for joining us, the audience. I thank Werner and Jerry, and especially Adriano. He saved the situation with the presentation at the beginning, and I have to apologize for the inconvenience because by this, but we could finally solve it. Thanks, Adriano. So thank you.
Okay. It's always tricky to work with this.
Yes, yes, yeah. And I would like to draw your attention to our next webinar. It's on the 6th of November. And we will have Scott Bryson, and he will talk about orbital farm, de-risking large-scale life support systems for space settlements. So I think we have an interesting topic, and by the end of November, we will have again Danielle Futzela from the Netherlands, and she will talk about imaginations of the secret of universe, because her new book has been released now today. The publisher called her that she got the first copy, so I'm curious to see the book. Thank you again very much, and I wish you.
Let me just add that we are filling up the calendar for 2024. Now we have dates up to May 2024, and we are talking with several lecturers that will bring on board quite interesting topics, like, for instance, the protection from cosmic radiation. There are advanced projects and studies about that.
Important topic.
And yeah, and other very, very interesting themes and topics that we will discuss. So
yeah.
Thank you, everybody. Thank you,
Thank
Sabine.
you so much. And last but not least, I would like to mention that we are a non-profit organization, that we are all working as volunteers here. Also our speakers, okay, in this case, they are part of our SRI, but they're also working as volunteers. So you can support us. Adriano will put in the chat
yep.
Our, you know, I give you the time to put it in the chat. You can support us by joining us, or put some donations if you have some money you want to donate. And yeah, you can join us also as volunteer or as a member of SRI. And of course, by joining our webinars and watching the webinars. So we hope that our community will grow. And I'm looking forward to the 6th of November and to welcome you to our next webinar. I wish you all a nice evening and yeah, goodbye.
Ad astra.
Bye.
Bye bye.